Good morning. The title of my presentation is Recent Progress in Modeling Wealth Inequality and Upward Mobility. My name is Bruce Boghosian. I'm on the Faculty of Mathematics at Tufts University near Boston in the US. I would like to begin by thanking the Collège de France and Professor Bouchaud in particular very much for their kind invitation to present this work. Let's begin with some motivation. Wealth inequality in the United States has increased pathologically in just the last 3 decades. Today, the 400 wealthiest people in the United States hold as much wealth as the bottom 200 million people, about $3.5 trillion. So when people speak of the so-called 1%, that does not even begin to capture reality. To restate the above statistic, the top 1.2 ten-thousandths of 1% of the US population hold as much wealth as the bottom 60%. This puts us in completely uncharted territory. By at least one major inequality metric, this is more unequal than France was in 1789 or Russia was in 1917. There is naturally the worry of political turbulence. But another reason that we should be worried is that wealth inequality is poorly understood. The kind of inequality I just described is not due to a Pareto power law distribution, a power law tale. It's also not due to an outlier effect or a black swan effect. In fact, it's easier to say what is not causing this kind of extreme distribution than what is causing it. Differences in wealth are not explained by differences in merit or hard work, by cleverness or intelligence, or in value to society. The net worth of Elon Musk is probably about 1 million times greater than that of a typical emergency medical technician. I think that even Mr. Musk would acknowledge that this is not because he works 1 million times harder, is 1 million times smarter, or is 1 million times more valuable to society. There is something more than meritocracy going on here that distorts the wealth spectrum at the very top. It turns out that the question of how wealth is distributed is both mathematically interesting and it touches on the very origins of inequality in the modern world. The first thing we should acknowledge is that although those of us who live in democracies instinctively regard equality as a normative state, wealth equality is in fact the very opposite of normative. Anybody who has played the famous game of Monopoly knows that it is a winner-take-all game. Everybody starts the game with the same amount of wealth. Everybody makes decisions they believe will benefit their own position in the game. The game involves some mixture of luck and skill. But in the end, a player wins by taking all of the wealth of all the other players. Free market transactions are not all that different from a game of Monopoly. In a free market, everybody makes decisions they believe will increase their own utility. Once again, a mixture of luck and skill is involved. So why do we find it so strange that wealth tends to concentrate in free market economies? The closest thing we might have to a controlled experiment in this regard might be the collapse of the former Soviet Union in 1991, which briefly gave rise to one of the freest free markets in recent history. The 15 republics of the Soviet Union were more or less forced to adopt what came to be called shock therapy economics. This involved rapid privatization of government-held assets and the lowering of regulatory barriers to businesses in general and to foreign competition in particular. Now, this sounds like a free market fundamentalist's dream. So what were the results? Economic destruction and mass emigration, a spike in the suicide rate, and lowered life expectancy, skyrocketing inequality, and ultimately, in at least 12 of the 15 former Soviet republics, an entrenched oligarchy. I actually saw this firsthand when I served as president of an American university in the former Soviet Union 10 years ago. These two houses are a 2-hour drive apart from each other, but as you can see, they might as well be located on different planets. Examples like this can be seen throughout the landscape of the former Soviet Union. So it's time to get down to mathematicizing this problem. To do this, let's first ask how to quantify inequality. One way to do this is with what are called Lorenz curves. These plot the fraction of economic agents ordered by wealth on the horizontal axis. On the vertical axis, we have the fraction of wealth held by those agents. And looking at the illustration on the left, we can see 3 interesting cases. First, if everybody in the society had the same amount of wealth, then the bottom X% of the population would hold X% of the wealth. So the Lorenz curve would just be the blue diagonal line you see here on the left. On the opposite extreme, if you had an oligarchy, a single person in the society who had all of the wealth and everybody else had nothing, in that extreme case, the Lorenz curve would be 0 until it reached the very right-hand side of the plot where it would jump abruptly to 1, as with the green curve on the left. Real societies have Lorenz curves somewhere between these two extremes, as with the yellow curve that you see on the left. In fact, the right-hand figure on this side shows the actual Lorenz curve of the United States in 2016. From the lower left-hand side of this figure, you can see that the combined wealth of the lowest 30% of the population is very nearly 0. And that's because many of them have negative wealth. On the opposite extreme, on the upper right-hand side, you can see that about 30% of US household wealth is held by a fraction of people so small as to be barely discernible on the plot. The Lorenz curve is equivalent in information content to knowledge of the full distribution of wealth. From it, we can define a metric of inequality that's known as the Gini coefficient. This is twice the area, shaded in yellow here, between the Lorenz curve and the diagonal. So for the case of complete economic equality we saw on the previous slide, the Lorenz curve and the diagonal are the same, so the Gini coefficient is 0. For the case of complete oligarchy, the shaded area would be the lower diagonal of the unit square, which has area 1/2, and twice that is 1. So as inequality increases, the Gini coefficient increases from 0 to 1. The wealth Gini coefficient of the US in 2019 is about 87%. In other words, 87% of the lower triangle is in fact shaded. The next thing I'd like to discuss is the kind of mathematical model that we'll be using. Mathematicians and physicists have a tendency to use idealized models. Sometimes these models are criticized by researchers from other fields, such as economics, for example, who have a tradition of using more elaborate models. In fact, I think both kinds of models have their role to play in the acquisition of scientific knowledge. Idealized models sometimes invoke what is called Aristotelian idealization, which calls for the stripping away of irrelevant properties. And sometimes they invoke what are called Galilean idealizations, which are deliberate distortions made to more clearly expose truths. We do this in physics all the time when we speak about point masses, surfaces without friction, or fluids without viscosity. The object is less to see how much you can include in the model and more to see what you can get away with ignoring. Models of this sort, which are sometimes called toy models, include famous models such as the Lotka-Volterra model of population biology, the Schelling model of urban segregation in the social sciences, and the Ising model of ferromagnetism, which I illustrate here. Briefly, about the Ising model, real ferromagnets consist of microscopic magnetic domains, as you can see in this micrograph on the left. And the collective magnetic strength of a ferromagnet as a function of temperature falls to zero precipitously at a particular temperature known as the Curie temperature of that material, named after Pierre Curie. In the 1920s, the physicists Wilhelm Lenz and Ernst Ising modeled these magnetic domains in a very simple way, in an idealized way, as a regular array of arrows, each of which can point either up or down. In the 1940s, the physicist Lars Onsager showed that Lenz and Ising's simple model of arrows pointing up and down, through mathematical analysis, give rise to the magnetization curve you see on the right. Now, shall we say that this model is bad because of the way that it drastically and unrealistically simplifies the magnetic domains? Or shall we say that it's good because it explains the qualitative shape of the magnetization curve, including the Curie point, reasonably well? History gives us the answer. The Ising model revolutionized our understanding of ferromagnetism in the 20th century. So clearly there's something to be said for simple models of this type. So in that above spirit, let me next describe the yard sale model of wealth exchange. This model was first introduced in numerical studies by Anirban Chakraborty back in 2002. It imagines a population of N, capital N, economic agents, each with some positive value of wealth. Two agents are chosen randomly to exchange in a transaction. Let's say those two agents have wealth W and X. The transaction conserves total wealth. So if the agent with wealth W ends up with wealth W plus delta W, then the agent with wealth X ends up with wealth X minus delta W in some transaction time, which we call delta T. Now, the sign of delta W is determined by a fair coin flip. It could be positive, in which case the agent with wealth W is the winner of the transaction, or it could be negative, in which case the agent with wealth X is the winner. The coin flip is modeled by the random variable eta. It's either it's either -1 or +1, and it has mean 0 because the coin is fair. That accounts for the sign of delta W. What about the magnitude of delta W? Well, what this model does is to restrict the magnitude of delta W to be a small fraction of the wealth of the poorer of the two agents, the smaller of W and X. And so it accounts for a certain amount of risk-averse behavior because it ensures that no agent's wealth can ever become negative. The proportionality constant goes as the square root of the transaction time delta T, which is natural for a stochastic process of this sort and gives you the right scaling behavior. After the exchange, two new agents are selected randomly and the whole process is repeated again. For a population of hundreds of agents, you might want to conduct millions or even billions of transactions of this sort until a steady state is reached. What is the ultimate result of this, the ultimate state of this system after a long time? Remarkably, even if all the agents start with the same amount of wealth, and even though the coin is fair, just as in the game of Monopoly, it turns out that one agent ends up with all the wealth. In fact, in the long time limit, a simple asymptotic argument indicates that all the other agents will see their wealth decrease exponentially. And moreover, the poorer the agent, the faster the exponential decay of their wealth. You can see this in the simulation on the lower left, which plots agent wealth on a log linear plot. All the agents begin with 1 unit of wealth, that's 10 to the 0 on this axis. In the end, the wealth of the wealthiest agent is approaching 10 units of wealth, while all the other agents see their wealth go to 0. The plot on the lower right here is an average of 10,000 independent runs, each one just like the one on the left. And that makes them smoother, so the approach to exponential decay, in other words, to more or less straight lines on this log linear plot, becomes evident. So the model results in oligarchy. In 2015, working with Merrick Johnson and Jeremy Mark at Tufts University, we confirmed this by proving that kinetic descriptions of this model, using either the Boltzmann or Fokker-Planck equations, saw the Gini coefficient rise monotonically, ultimately approaching 1. So the long time limit is indeed provably a total oligarchy. In 2016, Christophe Choreau of the Sorbonne showed that the statistical process describing this model actually saw the Gini coefficient approach 1 in the almost surely sense of probability theory. In other words, with probability 1. The Gini coefficient approaches 1. Though the model seems very fair, the initial equality between the agents quickly breaks down, after which there is an endogenous downward pressure on the poorer agents. Now, this downward pressure is just a trickle in any single transaction, but it's the kind of downward pressure which, if you multiply it by 7.6 billion people conducting quadrillions of transactions, that trickle becomes a torrent. And we believe that it's responsible for much of the poverty and inequality that we see in the world today. To justify this last statement, as I go forward, I will argue that as simple as this model I've described seems, the addition of 3 features to it is sufficient to describe empirical wealth data with remarkable accuracy, in the same way that the Ising model accurately described certain features of ferromagnetism. The 3 features we're going to add to this model are: first, redistribution of wealth; second, a bias favoring wealthier agents; and third, the possibility of debt. In this way, we will construct a theory of wealth distribution that has a completely unstable model at its foundation. There is no supply and demand balance, no stability except that provided by exogenously imposed redistribution. In other words, the model is nothing like neoclassical economics. It's nothing like expected utility theory. It's nothing like general equilibrium. So let's first make our first modification and add a simple model of redistribution. To redistribute wealth, we're going to take wealth from agents proportionately and distribute it back to them in equal shares. And we'll do this continuously in time. So in a time delta t, the amount taken from an agent with wealth W, we'll say is chi times delta t times W, where chi measures the magnitude of the redistribution. Notice that chi is a rate per unit wealth per unit time. So the total wealth that we collect from the entire society in time delta t is then chi delta t times capital W, where capital W is the wealth of the entire society. It's the sum of all the lowercase w's, the total societal wealth. What we then want to do is divide this into capital N equal shares. So the size of those shares will be chi delta t times capital W over capital N. But capital W over capital N is just the mean wealth of the society, which we denote by capital mu, by mu. Mu is the mean societal wealth. So now let's recap what we've done. We've taken a wealth chi delta T W from each agent, where W is their individual wealth, and we've given them back a wealth chi delta T mu. So the net amount that they've received is chi delta T times the difference of mu and W. And that gives rise to this new statistical process down here. One can see from this that, first of all, this change in wealth due to redistribution is completely equivalent to moving every household the same fraction of the way toward the mean. It is rank preserving. If you were the 10th wealthiest person before the redistribution, you will still be the 10th wealthiest person afterwards. And moreover, from the way that we've constructed it, it pays for itself. Remember that we're just giving back the total amount that we collected in the first place. And in passing, I can't resist pointing out that the US wealth distribution is so skewed right now that 85% of households are below the mean and would receive net wealth under this redistribution plan. This results, as I said, in this new statistical process that you can see in red here that includes both the yard sale model of transactions and this redistribution model. This modification results in stable wealth distributions that do not result in oligarchy. The higher the value of the redistribution parameter chi, the lower the Gini coefficient of the steady state distribution that results, which is something that you might have guessed. Well, it's nice that we've stabilized the distribution, but there's another flaw in the model as it stands. The coin should not be fair. In the words of the American essayist James Baldwin, anybody who has ever struggled with poverty knows how extremely expensive it is to be poor. Wealthier agents have higher percentage returns on investments, they receive better financial advice, and they're better able to evade taxation and utilize offshore financial instruments than the poor. Conversely, poorer agents have less time to shop for the best prices, and they pay higher interest rates on loans, and it's even been documented that they pay higher rent for equivalent real estate. Under these circumstances, it's unrealistic to determine the outcome by flipping a fair coin. In 2017, my group at Tufts University proposed a way to do this. We keep the statistical process exactly as it was, with yard sale model transactions and redistribution. But we sample the random variable eta so that its expectation value is equal to a bias B rather than 0, where the bias B for the agent with wealth W is proportional to the difference between W and X. If W is greater than X, B is positive and the agent with wealth W has an advantage. We normalize the difference, W minus X, first by dividing it by the mean wealth. Then there's a necessary factor of the square root of the transaction time in order to get the asymptotics right. And now we introduce a new adjustable parameter called zeta to control the level of wealth attained advantage. If zeta is equal to 0, we're back to the earlier model. In any one transaction, if W is equal to X, the coin is back to being fair. But by making zeta positive, we can tilt the playing field in favor of the wealthier agent in any transaction. The resulting model, including both redistribution and wealth attained advantage, is called the extended yard sale model, and its phenomenology is really fascinating. In particular, like the Ising model, it exhibits critical behavior. If chi is greater than zeta, in other words, if redistribution exceeds wealth attained advantage, the steady state Lorenz curve will reach 1 in the upper right-hand corner. So in this plot on the left, we have fixed the redistribution chi to be 0.2. For the first 5 plots you see here, zeta is less than or equal to 0.2. And sure enough, the first 5 Lorenz curves rise up to 1 in the upper right-hand side. If zeta is less than, sorry, that's what happens if zeta is less than chi. If zeta is greater than chi, in other words, if wealth attained advantage exceeds redistribution, then the Lorenz curve reaches only the ratio of chi over zeta. So if zeta is greater than chi, chi over zeta will be less than 1, and that turns out to be the final condition of the Lorenz curve over here. Now, this means that the remaining fraction, 1 minus chi over zeta of the wealth of the society, is held by a negligible fraction of the population, so that you get this jump in the Lorenz curve on the right-hand side from chi over zeta up to 1. So that wealth, 1 minus chi over zeta, being held by a negligible fraction of the population, is a situation which we would call a partial oligarchy. This phenomenon is actually called wealth condensation, and it was first described in a seminal publication by Professors Jean-Philippe Bouchaud and Marc Mézard in 2000. Another way to see it is to plot the wealth held by the wealthiest agent in a Monte Carlo simulation versus the ratio zeta over chi. When zeta over chi is less than 1, the wealth is in fact 0 to within some finite population size effects. And when that ratio zeta over chi is greater than 1, the wealthiest agent is then holding a finite fraction of the societal wealth. Using Bouchaud and Mézard's terminology, a fraction of societal wealth has condensed into the hands of the wealthiest agent here. Another feature of the criticality in this extended yard cell model that is also shared by the Ising model is the presence of what is called duality. So let's define the ratio of zeta to chi as a kind of temperature in the model. And we're going to call that capital T. We'll make T the ratio of zeta to chi. You can redo this argument replacing T by 1 over T, as you'll see, if you prefer to define it that way. But let's adopt this convention for the moment. The critical temperature, that where you get the first appearance of partial oligarchy, is T equals 1, where zeta is equal to chi. So to summarize what was on my last slide, when the temperature is less than 1, we say the distribution is subcritical without wealth condensation and without any partial oligarchy. When the temperature is greater than 1, the distribution is supercritical with wealth condensation, and it's partially oligarchical. Duality points out a deeper and very non-obvious symmetry going on here. Suppose you reverse chi and zeta. In other words, suppose you replace the temperature T by its inverse, 1 over T. This clearly has the effect of changing a non-wealth condensed state to a wealth condensed state, and vice versa. It was shown by Jia Li in work with me in 2018 that the Lorenz curve is exactly preserved under this interchange, aside from a vertical scaling to account for the wealth of the oligarchy. In other words, in this figure you see here, the solid curve here is a non-oligarchical state. It rises to 1 in the upper right-hand corner. The inversion of the temperature, or in other words, the exchange of chi and zeta from that state, results in the dashed Lorenz curve, which is a partially oligarchical distribution. You can see that a finite fraction of wealth over here is held by a negligible number of people. Remarkably, the solid curve and the dashed curves are exactly proportional to one another, and that is an exact result of the model. This fact leads to another remarkable result. We have a choice of how to analyze this model mathematically. We can do two things. One thing we could do is write down a kinetic equation, which is a partial differential equation for the distribution of wealth, which we'll call capital P. You can think of it as the probability distribution of wealth. This will be a kinetic equation for the full system. And in that case, we have to say that the presence of oligarchy is what would be called a weak solution to this equation. A weak solution is a generalized distribution that obeys the distribution theory of functional analysis that was developed by Sergei Sobolev and Laurent Schwartz in the mid-20th century. But it's a pathological distribution because it has this oligarchical component. It does not obey the rules of ordinary calculus. But we can do an alternative thing. We can split that kinetic equation into two parts. A partial differential equation, again, for the wealth distribution of the non-oligarchs only, in which chi and zeta are reversed, coupled with an ordinary differential equation describing the fraction of the wealth, which we'll call C, that is held by the oligarchs. This ordinary differential equation turns out to be what is called a logistic equation, and I present it here. You might notice from looking at it that it has two steady states. When zeta is less than chi, its stable steady state is C equals 0, which results in the rate of change of C being 0. But when zeta is greater than chi, its stable steady state is when C is equal to 1 minus chi over zeta, as we saw before. Again, this logistic equation for the wealth of the oligarchy is an exact result of the model, and this way of looking at the problem requires only the rules of ordinary calculus. This brings us to the third and final modification that we want to make, which is one that accounts for negative wealth agents. Our goal here is to solve the inverse problem. Since we have this model, given an empirical wealth distribution, we'd like to find the values of chi and zeta so that the Lorenz curve of the model most closely matches that of the empirical data. In doing this, however, we found it necessary to fit the empirical data not just to a single model distribution, but rather to an equivalence class of such distributions, those obtained by just rigidly shifting the model distribution to include negative values of wealth. The amount of the shift required, this rigid shift of the PDF, the probability density function of wealth, the amount of that shift is effectively then a third parameter of the model. And this 3-parameter model is then called the affine wealth model. This inverse problem actually has a side benefit that I'd like to point out. It gives a precise mathematical meaning to the term oligarchy. Without a model of this sort, without an underlying mathematical model, whether or not a Lorenz curve rises steeply enough on the right-hand side to be called oligarchical involves a subjective judgment. But with a model of this sort, we can do better. We can say that, well, our model has both non-oligarchical and oligarchical solutions. If the closest fit of the empirical data to the model results in parameters zeta less than chi, we can say that that wealth distribution is non-oligarchical. But if the closest fit results in zeta greater than chi, we can say that it is oligarchical. By this standard, the US and most Western European countries are oligarchical to varying degrees. This slide illustrates the 3 fits obtained using the affine wealth model to US wealth distribution data from 1989 on the left, 2001 in the middle, and 2013 on the right. In each case, the red curve is the empirical data, and the dashed blue curve gives the model results for the best fit. The average local error is shown in the inset, and in each case, it's only a few tenths of 1%. Similarly accurate fits have been found for European countries as well, the countries under the European Central Bank. Interestingly, we have found that most countries are near criticality. This is a scatter plot of fits in the chi-zeta plane for all the European Central Bank countries. Remember that criticality happens when chi and zeta are equal. And most of these points do lie near the diagonal. This is particularly interesting because some very recent work by Sam Polk and me at Tufts University shows that near criticality, the tail of the distribution is in fact not universal and rather depends very sensitively on the detailed redistribution model that is used. Finally, armed with this reasonably accurate model, at least it reasonably matches some empirical data, we'd like to turn our attention to using the model to elucidate calculations and draw conclusions that would have been impossible in the absence of a mathematical model. Now, we've already seen one of these. We can now say definitively, in a precisely defined way, whether a country is an oligarchy or not based on its empirical wealth distribution. A second example of what we can look at has to do with the calculation of what macroeconomists call upward mobility. One definition of this quantity is the probability that a person born into the bottom wealth decile will enter the top decile at least once in their lifetime. A more mathematically precise definition might be the expected time for an agent with some initial wealth, W0, perhaps at the midpoint of the bottom decile, to achieve a wealth, W1, perhaps at the bottom of the top decile, for the first time under current economic conditions. This is called the first passage time to reach W1 from W0. And it makes sense, even if it's much greater than a human lifetime. Since this quantity is itself a random variable, it would be even better still to know the full distribution of first passage times rather than just the expected first passage time. Upward mobility takes place on timescales, as it turns out, that are much, much longer than those of the natural evolution of the wealth distribution. Whereas wealth distributions that respond to a shock, such as, for example, the collapse of the Soviet Union, might settle down in a matter of a decade or less to something new and more or less stable again. But upward mobility characteristic times can last for centuries. And macroeconomists have known this for some time. This study that I'm showing an illustration of here, of the persistence of wealth among the wealthiest families of Florence, Italy, is about 5 years old. It demonstrates using tax records obtained from the year 1427, comparing them with current tax records, and using the fact that Italian surnames tend to be specific to geographic regions in Italy. The researchers were able to conclude that the 1,000 wealthiest families in Florence in 1427 are pretty much still the same 1,000 wealthiest families in Florence today. Similar results have been obtained for other countries as well over other time intervals. In Japan, the descendants of samurais are more likely to be doing better economically than those who are not. The mathematics of first passage times provides an accurate way of quantifying this kind of result. And that's what I'd like to describe in the remainder of my talk. To illustrate first passage times in a familiar context, let's first consider a simple game of the sort that is taught in many introductory probability courses. Let's say that Alice and Bob both begin with W euros, so that the total wealth of this population of two people is 2W. The state of the game is specified by the number of euros held at any moment by Alice, which we'll call A. If Alice holds A euros, we know that Bob holds 2W minus A euros because wealth will be conserved in this game. A fair coin is repeatedly flipped. If it comes up heads, Bob gives a euro to Alice. If it comes up tails, Alice gives a euro to Bob. The game ends the first time A reaches either 2W, in which case Alice wins, or A reaches 0, in which case Bob wins. Provably, one of these two outcomes will eventually occur with probability 1, and when it does, the game is over. Let's suppose the time required for this is called tau. What is the distribution of tau? What is the expected value of the length of the game, the expectation value of tau? Well, let's suppose that the starting amount for both Alice and Bob is 5 euros. And we're going to show this, illustrate this by comparing it to a random walk below in this animation. Notice this is a winner-take-all game. Let me run the animation next. So Alice's wealth started out at 5, executed a random walk, and remember, the game is over when it hits either 0 or 10. In this case, it hit 10 after 43 time steps. So that was the first passage time for this particular game. The expectation value of tau can be worked out using elementary methods of probability for this game, and it turns out to be W squared. So in other words, for this game, it would have been 25. Notice that 43 is quite a bit greater than 25, so you might conclude from that that the standard deviation is also large. And in fact, it is. The standard deviation of this is W minus 1 quantity squared. So some games will last for a very long time, others will last for a much shorter time than the expected value of 25 time steps. So, and also the distribution of tau turns out to have an exponential tail in this case with this long expected value. Is there a way to obtain similar results? This is an extremely simple model. It's sometimes called the gambler's ruin problem, and it's a classic problem of probability theory. Is there a way to obtain similar results for first passage times for our reasonably accurate models of wealth distribution? Well, as mentioned, we have kinetic equations for the extended yard cell model and the affine wealth model. These kinetic equations encourage us to think of the problem in a particular way. Up to this point, I've not presented, and I really won't present the kinetic equations for these models in any detail. I've alluded to them, and I'll say a bit more about them now. They encourage us to think of the problem of finding the distribution of a single agent at time t, let's call it alpha of W of t, given that it started at some place W0 at time 0, and that it's transacting randomly with a background of other agents that have a distribution capital P. Here's the form of the equation. Now, for those of you who've seen this kind of thing before, it's called Kolmogorov's forward equation or a Fokker-Planck equation, depending on whether you're a mathematician or a physicist. The quantities sigma and d are called the drift and diffusion coefficients, and in square brackets, we've denoted the fact that they do depend on the background distribution P. Now, notice that this is a linear equation in alpha, if you know the background distribution P. In the long time limit, if we start this test agent, this test walker somewhere at some initial wealth W0, the number of places it could end up at, which is represented by alpha of W and T, that distribution will spread out over time. In the long time limit, we expect that alpha will be equal to P. That is, the distribution of the single agent diffusing in this background will be the same as the collective distribution of the background after a long period of time. In order to figure out the background, then, you can simply replace the evolution of the background. You can simply replace alpha by p, and that will give you a nonlinear equation for the background p. If we solve that correctly, and we've developed lots of practice at doing this using different numerical methods, we should be able to simulate the convergence of alpha to p. Now, in doing this, we'll take p to be a steady state background distribution, and we're letting the distribution of the test walker, alpha, converge to it. So here's the situation set up as an animation. We have a background distribution, which we see in blue. The single agent is known to start at a particular value of wealth W naught, which in this case is 1. And we're going to let it evolve in time. And you'll see in yellow all the places where this test agent can evolve to from its initial wealth. And in the long time limit, its distribution converges to the background distribution P after some time. So now, to obtain a first passage time, we see what we have to do. We fix the background distribution P, that blue curve in the previous slide, which I'm not showing in this illustration so as not to confuse things. We obtain this background, this steady state background P, by solving the nonlinear equation I described on the previous slide. And now we're going to start a test walker at an initial wealth, in this case at 0.3 of wealth. And we're going to stop it when it reaches a target wealth. Now, this target wealth, W1, is 0.9 in this case. And in order to do that, what we're doing is letting the distribution alpha spread out, but demanding that it goes to 0 when it reaches the target wealth, W1. It's a boundary condition for this diffusion equation for alpha, reflecting the fact that once the individual diffuses to this last point, they will have achieved first passage and are thereupon removed from the system. So we can do that by putting a 0 boundary condition on alpha at the right here. We can then examine the flux of the agents that are crossing the boundary at that point. Alpha may go to 0 at that point, but there'll be a continual outward moving flux. And we'll plot that flux on the right here. We can then reinterpret that flux of agents as a probability distribution of first passage times. So here's what the simulation looks like. You can see that the distribution of alpha spreads out, and we stop it before it decays. Eventually it will decay to 0, but as it's decaying to 0, the flux of agents leaving here is being plotted here. Let me try to show that again. Now, the flux crossing the boundary W1 versus time is in fact the distribution of first passage times. It starts small because initially there's no age, the agent hasn't had a chance to diffuse over there. It reaches a peak and eventually it goes to 0 because the distribution alpha will go to 0 because all these agents are leaking out on the right. So the key point is that we can reinterpret this flux versus time as the distribution of first passage times versus time. And we can go ahead and take its first moment to get the expected first passage time. If there are probabilists in the audience, I would note that the calculation can also be done using Dinkin's theorem of probability theory if all you want is the expected first passage time. If you want the full distribution, this is a good way to do it. In this way, we have computed the expected first passage times for agents beginning in the middle of the ith decile and ending at the bottom of the jth decile, moving in a background of real US wealth data in 2016. And the first passage times are shown in this table with the times converted into actual years. Now, many of the first passage times toward the right are much longer than a human lifetime, and this begins to get at the reason that persistence times for wealth can extend into centuries. But it should be kept in mind that the standard deviations of these distributions are almost as large as the means themselves sometimes. So this is certainly not to say that it's impossible to achieve these transitions in one human lifetime. It certainly is. Many people do so, of course. It's possible to go from the first decile of wealth to the seventh or eighth decile of wealth in a human lifetime. It's difficult to do this, however, and that difficulty is reflected by the fact that the times given in years on the right-hand side are so large. In fact, I've not even shown the times required for the attainment of the 9th and 10th deciles because they are extremely large and difficult to calculate for that reason. Still, this kind of calculation has important ethical ramifications, especially in countries where, for example, the quality of one's healthcare is correlated to wealth. If this is limited by circumstances that occurred centuries earlier in one's ancestry, there's a clear ethical issue. This has ramifications for discussions about reparations for slavery and genocide as but two examples. While, again, the evolution of wealth distributions takes place maybe on a matter of decade-long timescales, wealth persistence can last for centuries. In conclusion, I'd like to maintain that the yard sale model and its variants are simple mathematical models of wealth distribution that exhibit remarkable accuracy. In spite of their simplicity, some of these models, such as the extended yard sale model and the affine wealth model, provide real insight into the origins of inequality. These models challenge the economic orthodoxy of supply-demand equilibria, positing instead a completely unstable foundation for wealth economics in which redistribution is the only mechanism preventing oligarchy. Models of this type that are shown to be faithful to empirical wealth data can be used then to extract other macroeconomic parameters, such as upward mobility and its relation to inequality, that could not be extracted without the framework of an underlying mathematical theory or model. We expect that models like this one will be improved over time, but I think it's already safe to say that they indicate that we need to rethink our attitudes about wealth economics in very fundamental ways. This work has implications not only in the mathematics of inequality, but also, I think, in economics, politics, public policy, urban planning, and ethics. And I thank you very much for your attention.
Thank you very much, Bruce. This was a fascinating talk, and I am sure people will have enjoyed it. I have a few remarks and questions for you. The first comment is, I remember the first time I presented the work that you were kind enough to cite at a Santa Fe conference with physicists and economists. Economists began being very nervous about the model because they called it a model of steel. They thought that these type of exchanges where one agent loses and the other one gains is stealing. You know, the idea is that a transaction is something that's fair, that if someone buys, it's because he thinks or she thinks that what he's buying or she's buying is worth it. So it's a completely different framework, obviously, where you discard the possibility that interactions are actually unfair on average. I mean, they might be fair, they might be fair on average, but on a single case basis, they might be unfair. But anyway, I was interested to hear about your reaction if you had the same type of comments or questions. What do you say when people come up and say, you know, this is not a model because it assumes that transactions are unfair, and this is not true in the real world?
I've presented the model to economists, and I have many economists that I consult with that maybe more heterodox economists who keep sort of an open mind about this, I understand where they're coming from. The models that prevail in economics today are models, for example, like expected utility theory and general equilibrium theory, that assume that there are utility functions, and people act to increase their utility. And in the work of Arrow and DeBrew, for example, in the 1950s, it's shown that this leads to a optimal transaction outcome in which there is a price that is agreed upon by both parties. If the two parties don't agree on the price, then the transaction won't take place. And if both utilities aren't increasing in the sense of Pareto optimality, the transaction won't take place. Mathematically, the presence of those utilities gives you what a mathematician would call a Lyapunov functional. Those things, if they must increase to their maximum value in the course of the evolution, you will reach a steady state, and you'll reach the steady state without any redistribution at all. So I think that's where economists are coming from. There are a number of ways to respond to this. This, in fact, is related to the PhD work of one of my PhD students, Jeremy Mark. But one way that you can respond to it is by saying that while this may be true for the sort of neoclassical deterministic models like expected utility theory and general equilibrium theory, it's not true for behavioral economic theories, such as the work of Kahneman and Tversky on prospect theory. Prospect theory does not assume that agents have a built-in utility function. In fact, the existence of innate utility functions in people is questionable due to the Allais paradox that was pointed out prior to prospect theory and was one of the motivating factors leading to prospect theory. So if you look at agents that behave using behavioral economic theories, and these are agents that exhibit maybe more human qualities like risk averseness, you won't find this kind of Lyapunov functional guaranteeing a steady state. In fact, in some ways, the yard cell model can be thought of as a very simple approximation to prospect theory. So
okay, yeah. So, but maybe something that would make the model more palatable also is that is the inclusion of growth, because as you say, the model conserves wealth, but clearly, you can argue that exchange is also creating wealth. And so have you considered generalizations of the model where each transaction actually creates wealth, which may be unequally distributed between the parties, and therefore perhaps include the fact that GDP is exponentially growing with time on long time scales, and maybe the fact that it's not a systematic fact that every transaction leads to a loss for someone and a gain for someone else. Maybe both of them gain, but at an unequal rate. I guess my feeling is that you can preserve a lot of the mathematics of the model doing that.
Yes, I think that's true. And no doubt, this is far from the last word in models of this sort. And no doubt models like the one you're describing. Well, first, there are some models like the one you're describing already, and I'm sure that others will come along. If the growth is sort of distributed among the agents according to their current wealth distribution, then it won't change anything. But as you point out correctly, it's not distributed that way. It's the addition and of wealth due to growth will not be distributed in the same way as the current wealth distribution. The other thing that one must take into account, if one takes into account growth, is consumption. And that is likely to have yet a different distribution versus wealth. There's very nice discussion about this in a book, which I just happen to have next to me here, called Interacting Multi-Agent Systems by Peresky and Toscani. And there's chapters on this that I highly recommend.
So my next question is about the Yaw-Sale model, where you assume that delta W is additive, and then you have this trick to avoid any wealth becoming negative. But wouldn't it make more sense to take delta W as kind of multiplicative rather than additive somehow?
The change in the change in wealth.
That is, you would say that when two people meet, the poorest one only engages in a fraction of his wealth.
Yes, yeah, which is multiplicative in a sense, because delta W is proportional to the wealth of the poorer of the two agents.
Oh, yes. I'm sorry. That's exactly your model. So maybe I misread this line. Yes. So it's already the case.
Yeah,
okay.
I think the
sure.
rationale
for
that.
My bad.
No worries. The rationale for that is sort of, if I'm engaging in a transaction with Jeff Bezos, the amount at stake will be a fraction of my wealth.
Sure. No. But that would, yes. It seemed clear to me, but indeed that's how the model works. And then another technical question, which I found very interesting, is that you find that for any distribution of, you insisted on the fact that for any distribution of the non-condensed part, you get a logistic equation for the condensed fraction C. Do you have an intuitive interpretation of this logistic equation? Where does it come from?
It certainly, let me go back to it here if I can find it. There it is. It certainly gives you the right behavior. What it's saying is that this transition from subcritical to supercritical, from non-wealth condensed to wealth condensed, is a transcritical bifurcation. This is actually true even if chi and zeta are functions of time. It has the right to steady states, one for the non-oligarchical case and one for the oligarchical case, and they stabilize and destabilize just where you would expect. The thing I thought was most curious about this when we first arrived the result was that it doesn't depend on the non-oligarchical part of the distribution, except via the total wealth of the non-oligarchical part of the distribution, which is 1 minus C, essentially. So you can write a closed equation for C that doesn't depend at all, a rate equation for C that doesn't depend at all on the non-oligarchical part of the distribution. C certainly enters into the non-oligarchical kinetic equation, but the little p, the lowercase p, from the non-oligarchical part of the distribution doesn't enter into the equation for C, because from the oligarch's point of view, they are so much wealthier in this limit than everybody else, that everybody else from that perspective is just sort of lumped into one unit of wealth, 1 minus C. The other thing you can see from this is the only thing that limits the wealth of the oligarchy is redistribution. But we were surprised and delighted when it turned out to be a logistic equation. And it's an exact result of this nonlinear model. There are no known completely time-dependent solutions for capital P in the full model. So the fact that the oligarchical part gave rise to a something that you can solve analytically was surprising to us. Aside from the fact that it does have all the right behavior at the end of the day, I don't have I can't compare this, for example, to logistic equations for population growth or that sort of thing.
Yes, that's what I was looking for. I mean, to have a kind of direct interpretation of the fact that there's a linear growth for small c and a saturating minus c squared behavior. I mean, there must be something simple to extract from this equation, but I can't find it right.
Population growth, one would call the carrying capacity or something like that.
Yes.
But yeah.
Okay, and my final question is maybe more philosophical, is that I think everybody would agree that a Gini coefficient of 0 is not optimal, and a Gini coefficient of 1 is not optimal either, and is clearly not morally desirable either. But something that has been obsessing me for many years now is, would there be any rationale for finding an optimal value of G? What would be a prescriptive kind of objective way to say, well, this society is roughly, acceptable in terms of its inequalities? Have you thought about this? Do you think there's a guiding principle to decide whether G is too large or too small, or is G actually not the right measure? And it's more what you introduced, this idea of being able to define the presence or the absence of an oligarchy that matters most.
Well, to answer the second question first, I do think that the presence of even a partial oligarchy is a drain on it's sort of a parasitic drain on a society. I think that one can have a robust meritocracy without having a partial oligarchy or claiming that these are the job creators and the innovators and so forth. That distortion of the wealth spectrum at the top due to a partial oligarchy, I can't imagine any circumstances under which I would say it's ethically justified. But I do agree that a Gini coefficient of 0 it's impossible even if you wanted it, and there are good reasons for not wanting it. But likewise, there's problems when the Gini is too high, and in the United States today, 87% is exceedingly high. The work that I'm aware of that most, I think, closely relates to your question is this beautiful work of Ariely and Norton about 10 years ago, I want to say, in which they asked people in the United States what they thought the wealth distribution was in quintiles and what they would like the wealth distribution to be in quintiles. And they allowed them to move around the quintiles to reflect what they thought the wealth distribution was and what they would like it to be. And all of them chose something. Well, I have to say the key point that gets to the ethics of it is they used a methodology that's due to the American philosopher John Rawls called the veil of ignorance, where you ask people to choose the wealth quintiles, but you tell them that, forget about whatever wealth you have now. You're not going to bring it with you, and we're going to drop you into this society randomly sampled from the quintiles that you choose. And when people had to choose what the quintiles would look like, with that in mind, with that veil of ignorance in mind, that they don't know where they're going to end up. They're going to be sampled according to the distribution they choose and dropped into the society. They became much more reasonable with how much wealth inequality they would like to see. And all of them chose an amount of a distribution of wealth that was more equitable than what they thought the distribution of wealth is. The punchline of the study, though, is what they thought the wealth distribution of the US is in quintiles was far more equal than what it actually is. If you search on Ariely and Norton, you'll find this study, and that's maybe one way of approaching the question.
Well, it's interesting you quote Rawls, because that's what I was about to ask as well. Isn't there something missing in all these models, which is again coupling growth in a sense to inequalities, in the view that Rawls would say that inequality is acceptable insofar as it benefits the poorest. And so I think that trying to find a way to couple, inequalities to growth, because the intuition is that G equals 0 is not optimal, because probably it would lead to everybody getting poorer in the end. And so my impression is that a very interesting area of research would be to try to couple these type of models to a model of growth that would couple inequality to growth and maybe lead to something more, as I said, a kind of guiding principle to try to know whether G is too high or too low.
I completely agree. I think that there's much more to be done with models like this. As I said earlier, these are certainly not the last word on these kinds of models. I think there's still a lot of interesting things that can be added to models like this, and lots of qualitatively interesting things left to discover.
Well, Bruce, thank you so much. I hope this talk will be inspiring to people who will have listened to it on Wednesday. I mean, when it's live, and also later on, because as you know, these lectures will remain on the Collège de France site for a long time. So I hope people will enjoy it for years to come. Thank you very much, and I hope to see you in better conditions.
Likewise, thank you very much for inviting me, Jean-Philippe. It was a pleasure, and I likewise look forward to seeing you under better conditions.
Goodbye.
Bye-bye.